Aloha. This is Assistant Professor Pike again. We're talking about refrigeration example. This time we're going to be doing multiple refrigerants in a parametric table. So I edited this a little bit, just put in multiple refrigerants and all of the front matter, all the given information, the discussion about what we're doing is the same. So I left that in. The big difference of what we're going to do today is we're going to put individual variables in instead of variables in an array. So instead of them showing up with the square brackets, we're going to have to use a different method of putting them in because we want to run parametric tables. So the first thing I want to do is, in recognition of the fact that we're going to be doing a parametric table, but I want to be able to test it without the parametric table. So we'll put in this directive. If it's not a parametric table, so $, if not, parametric table, R12, that's our selected refrigerant. End if. So if we want to just do a calculation, we can click up here, and if we want to do the parametric table, we'll look at that a little bit later. We'll do the calculation for the table. There's a table calculation right here. Solve table. Or we can go to the table itself, which is what I normally do. In the meantime, that sets us up for that capability. And we will now put in the modified program using a different method for the variable identification. So since they're not going to be array variables, what we do is we put an underscore because that puts the variable as a subscript. You could just do T1, T2, but I like the look more of the subscripts. So here we have, that's a T underscore 3, gives us the subscript. T square bracket 3 close square bracket also gives us the subscript, but it puts it into an array instead of into the program itself, or the solutions window. So those will show up eventually. We don't have a solutions window yet because we haven't solved anything. And so for every one of these steps that we had before, we have all the variables converted to individual variables. So notice over here, the way it was previously would be H and then just empty square brackets. Now we have an individual variable for each state point instead of an array variable. So the next thing I want to do is take all of these commented out items and put them into the diagram window where I've already pasted in the diagram for the system that we're looking at. So we'll start with superheater temperature, and we like to have that, I like a darker red as we discussed previously. And T superheat, let's go 14 point. One thing you'll find is the numbers in here, the size of the font in here varies dramatically. Sometimes 30-point font is too small. It's a function of the magnification of whatever diagram window you're working in, and all you have to know is that if the font size is too small, you just change it, or too big, vice versa. It's not a big issue. It's just don't necessarily expect it to look like a 14-point font. But we've got the T superheat. We're putting that in, and that's not a bad size, so we'll stick with that. We'll move on down the line, and we don't want to do that yet because, as we previously discovered, this was highlighted, it was going to write over it, so we don't want to do that. So now T4 is the next variable we want. So we'll go T4. Okay. P2. Input variable, P2. Okay. T subcooling. T subcooling. And I'm still highlighting. Gotta get out of that. And the way you know that is it doesn't come up to here and automatically default to text. If it comes back and is already set up for an input variable, it means you probably still have it highlighted, even if it's covered by your selection window here. So we're looking at T subcooling. Put that in. And do we have any more inputs? Yes. Q dot. And we're going to put we have to get out of here for a second. So we're going to go back over here and we're going to change. No, we're good. So Q dot. So Q dot evaporator. Rate of heat in the evaporator being absorbed. So we call it a 2-ton unit, as we recall. So we'll say input variable Q dot evap, rate of heat being removed. Okay. And now we need to go back to, so I want this to be, I want to duplicate, I want to make a copy. Because I want to do what we did before, which was, so we're going to make this an output variable. Output variable, and we're going to put that in a nice green color. Okay, italicize it just because I feel like it. Okay, and now let's go back to our variable info. We need to reset, we need to set the units for everything. So now we've got BTUs per pound. What we can do is just like an Excel spreadsheet. This little square here, click on that, drag it down, and it will fill down all those information. M dot is kg per, not kg, lb m per hour. Pressure, PSIA. This is specific heat, so that's BTUs per lb m. This is BTU per hour and refrigeration ton. So ton, okay. This again is BTUs per pound mass. And so is that one. Next one, BTUs per pound mass, specific heat. Our S, we're going to use Fahrenheit instead of Rankine. It works out the same, but again, occasionally you'll get some issues for units because you have something in Rankine versus Fahrenheit there. So we'll eliminate that potential. Fahrenheit. V is specific volume, so it's feet cube per lb m. It's the reciprocal of density. B dot is feet cubic feet, per hour. And this is going to be in GPM. We're converting it to gallons per minute. Work of the compressor, specific work, BTU per pound mass. W dot, work of the compressor, the work rate of the compressor, which is power, HP. And that takes care of all of our units. So the next thing we want to do is come back here, put in our variable information, which that was P2 was 141. Subcooling was 5 degrees. And this was, we want this to be tons, but it says BTUs per hour right now, so I have to change it to the alternate units so we can put in tons. So if we go to, cancel that, I want to edit this, show units, show alternate units, okay, 2 tons, notice it did that, and this shows up, and we want it to show up anytime, not just after calculation. So we've got 2 tons, but for our calculations it's going to use, because it's our primary unit, 24,000 BTUs per hour. Otherwise we have to do conversions. So this works out well. Now let's see if we do a run. Now we've got all of this information. We've solved all of our data. And we can look at that, but we're not going to take the time right now. What we want to do is we want to build a parametric table now. So to build our parametric table, we come up here and we say new parametric table, and we want to put in variables. We're going to vary the refrigerant, so that's going to be a variable that will actually enter the information, and everything else is going to be calculated. But we want to compare, and we want to see our Q evap, the work of the compressor, the condenser specific heat, the COP, the power required by the compressor. And let's get our flow rate in gallons per minute, and let's also add in our mass flow rate. So now we decide we want these variables in here. All of these below the $, our fluid variable, are calculated. We've already set up the calculations. We'll say okay. So now what we want to do is put in our refrigerants. We want R12, R134A, R717, which is ammonia, and R1234YF. And we will delete the rest of these because we don't need these runs. All after row 4. Okay. So now we've got all our variables that we want, our refrigerants, and we can calculate by clicking on this green triangle or on this solve table, either one. Well, I think there's a function, yeah, F3. I'll usually do it here because it's right there. And look at that. So now we can compare each of our cycles based upon refrigerant. So how much heat per pound? Notice most efficient per pound are ammonia. And the work of the compressor per pound, BTUs per pound, how much heat is being added there. And the condenser, how much heat is being rejected, which needs to be the sum of these two, right? But we calculated it separately, and we did a check calculation previously. So that's all I wanted to do, to show you. Now we have a way to look at, on a table, all at the same time, each of these different refrigerants. Thank you. So that sums it up for this. If you like, you could go in and put the data in here. One other thing we will do, though, is look at the solutions window. So what we want to do is notice table 1, run 4. So in the solutions window, when you run a parametric table, it shows you the last run. But what we also want to do is set up in as a key variable, and we'll highlight them so they stand out a little bit, the ones that we're looking at in the table. So we got the what the refrigerant is, and notice now we just had main before, and now we have a key variables item. So we have a key variable refrigerant, so we can go back and we can add in the rest of the ones that we were looking at. So we had Q evap, right click, key variable, highlight it, okay, specific work of the compressor, we'll add that. And we didn't add a key variable. Let's do that. Okay. Then we want specific work of the condenser. Key variable, highlight it. Okay. COP. You can also add text in here. The last one, or actually it's for, let's just say for current. Refrigerant. Just so you can see what happens. If we go back to key variables now, it adds that text in. So you can put text in for any one of these. You can add it at any time. You just right click on it, pulls it back up, and you can add whatever text you want. Okay, so this is for Q evap. So specific heat rejection in the evaporator. Okay, so now that'll show up there. Now we can go back and finish it up. COP, we also added the work of the compressor, the power required actually by the compressor. Right click. So that's the work rate. We went ahead and put that in horsepower. We can make alternate units too if we want. We put kW, and it will do that for us. Okay, notice it immediately does the conversion, and it will also show up here. Kind of convenient. And the volumetric flow rate in GPM. Make that a key variable. Okay. And the mass flow rate. Last one, m dot. Let's go ahead and put kilograms per second, because that's a typical mass flow rate in the metric system. Make that a key variable, just to show you again. Alright, so it's not that very many, not a high mass flow rate compared to some we've seen. And now we've got all the variables that are in the table. For the parametric table, we have them showing up here. And we can put whatever comments we want. We can also insert a separator, put this line wherever we want, right after the refrigerant, for example. We can move them around. That's it. Thank you for your attention. I think you've got a lot to play with at this point.